Swayam Prabha. Digital India. Educated India.
Welcome to the next lecture of ionic polymerization. Now, before we proceed further, let us have a look at what we studied previously. We studied various classification scheme for ionic species. We discussed about the effect of solvents during the ionic polymerization. Apart from this, we discussed the ionophores, the concept of ionogenes. We discussed about the various ionic pairing systems. We discussed about the covalent species. We had a discussion about the equilibria between the free ions and ionic pairs, and we developed the mathematical equations related to the conductance studies. We discussed about the heat and entropy dissociation of various ionic pairs and described the various type of ions. We had a discussion about the initiation and propagation in ionic polymerization and the effect of solvating agents in ionic polymerization. Now, in this particular chapter, we will discuss about the cationic polymerization of carbon-carbon double bond. Now, this particular thing, the cationic polymerization plays a vital role when we try to develop the industrial polymers for various specific uses. Now, in this category, we will discuss about the protonic acid. Now, protonic acid or Bronsted acid, they usually initiate the cationic polymerization by protonation of the olefins. So, this particular aspect in the basic chemistry is being widely used in the refinery system, especially in the process of polymerization. So, under this head, the acid should be strong enough to produce the sufficient concentration of protonated species. Now, have a look of this particular reaction number 1. Here, this HA, this reacts with this particular compound to give you this ionic species. The anion of the acid should not be highly nucleophilic. Otherwise, what happen? It will terminate the protonatic olefins by combination. So, if you recall that in the previous lectures we discussed about the deadness of those active polymer chain. So, it may dead the polymeric chain, so that the desired effect you may not be able to achieve those desired results. So, this is one of the example of this such type of thing. Now, the ionic species usually do not exist as a free ion, but as ion pairs. So, if you recall that in the previous lecture we discussed about the concept of ionic pairs. Now, the interpolation around the anionic portion is used to specify that the negative counter ion remains close to the positive fragments. Now, however, it should be remembered that the free ion coexist with the ion pair, and their relative concentration conclude the overall rate of polymerization. So, this usually this relative concentration play a very vital role in the overall rate of polymerization. Now, let us have a look about the cationic initiator. Now, cationic initiators are equally important as compared to the protonic initiator. Now, the requirement for the anion not to be excessively nucleophilic generally limits the utility of most strong acid as a cationic initiator. Now, hydrogen halides are usually ineffective as initiator of cationic polymerization because of highly nucleophilic character of halide ions. So, that must be very selective things when we discuss about the nucleophilic character of various compounds. Now, hydrogen iodide, this shows some tendency to initiate the polymerization of the most reactive monomers. like vinyl esters or vinyl carbazole, etc. So it seems some tendency. Now, apart from this, the Lewis acid also play a very important role in the cationic polymerization. There are various Lewis acids being used to initiate the cationic polymerization, and generally at low temperature with the formation of high molecular weight polymer in high yields. So, these includes metal halides, AlCl3, BF3, SnCl4, SbCl5, ZnCl2, sometimes TiCl4, and their organometallic derivatives. Sometimes these organometallic derivatives also play a very vital role. One of the best organometallic derivative is termed as R3Cl. So, Lewis acid, they are most important means of initiating cationic polymerization. Aluminum, boron, tin, titanium halides, these are the most frequently used Lewis acid. So, this promotes the cationic polymerization. Now, initiation by Lewis acid is almost or you can say the always requires to proceed much faster in presence of either proton donor, sometimes referred as protogen, sometimes you may call the water, hydrogen halide, alcohol and carboxylic acid as the proton donor. Sometimes carbocation donors, cateogens, they are also required, such as alkyl halides. One of the best example is butyl chloride, triphenyl methyl chloride, then esters, ethers or anhydrides. So, they play a vital role. Now, the initiation process of boron trifluoride and water is usually given by this boron trifluoride plus water. This gives this BF3OH2. Now, this BF3OH2 is further reacts with CH3 twice C double bond CH2 to give you CH3 thrice C plus BF3OH minus. Now, the initiator co-initiator complex, this is BF3OH2, is often shown as H plus BF3OH. So, this is again a very good thing to be noted. Now, initiation by aluminum chloride and tertiary butyl chloride is usually described by this particular reaction, AlCl3 plus CH3CCl4. Now, CH3C plus AlCl4 minus. Now, here this CH3C CH3 whole thrice C plus AlCl4 minus reacts with this CH2 double bond CH2 to give you CH3 whole thrice C CH2 CH, and this phi represents the phenyl ring, phi AlCl4 negatively charged. Now, the initiation process, and sometimes people may ask that how we can generalize this initiation process in cationic polymerization. So, this initiation process normally can be generalized by this initiator plus Zy. This is the rate constant, y plus Iz negatively charged, then y plus Iz, it may react with a monomer. This is the rate constant, then Ym plus Iz minus, where I, Zy and M, they represents the co-initiator. This is the initiator and the monomer respectively. So, this is the basic chemistry behind this initiation process. Now, initiation by a combination of a Lewis acid and protogen or cation has the advantage over initiation by Bronsted acid, that the anion Iz minus is far less nucleophilic than A. Now, this prolongs the life of propagating carbocation and allows the propagation to proceed to the higher molecular weight. Now, initiation by the combination of an alkyl halide and the Lewis acid, this can be achieved by using the hydrogen halide and a Lewis acid. So, the alkyl halide thus produced in situ by addition of hydrogen halide to monomer followed by the reaction with the Lewis acid. Now, usually there is an evidence that Lewis acid initiate a slow polymerization in some cases or some system, but very rarely or not in the most of the system. Now, usually this slow polymerization system by a self-ionization process in addition to the co-initiation process. Now, self-ionization process is again very crucial or very important in the cationic polymerization. Now, people have suggested the two mechanisms for the self-initiation. One involves the biomolecular ionization, that is represented as twice Al B3, Al Br, sorry, this is Br 2 plus and Al Br 4. Now, this followed by the reaction with a monomer. Now, because when you produce this initiator, then you can react with the monomer to give you this species. Now, see here, this is reacted with one monomer and gives you this ionic species. Now, the Lewis acid acts as both initiator and co-initiator. The second mechanism which we were talking about, this involves the addition of Lewis acid to monomer followed by the reaction of the adduct with the another molecules of Lewis acid. You can see here that this BF3 plus monomer can react with this and form this BF2M, and further if it reacts with BF3 gives you BF2M plus and BF4 minus. The most of the evidence to support the self-ionization process is indirect and consisting of kinetic, conductance and spectrophotometric data for the polymerization at different levels of dryness and purity. So, one can conclude that the self-ionization occurs if polymerization is achieved in system that is subjected to the most stringent purification and drying protocols. The major problem which people may face in ascertaining whether the self-initiation occurs and if it does, its extent relative to the initiation process involving a co-initiator. Now, this is the large effect exerted by the small amount of protogens or cationogens. So, usually when we take one example, that water concentration of say 10 to the power 5 m are sufficient to increase the initiator rate by a factor of 10 to the power 3 for TiCl4 and AlCl3 in CH2Cl2. Now, another thing is that which is very important, that is the sterically hindered pyridines, or sometimes referred as SHP. Now, sterically hindering concept is again important. That means one particular segment is usually hinders the formation of other one. So, they are generally active proton scavengers, but they do not react with any kind of Lewis acid or carbocations. You may say in other words that steric hindrance, they cuts down the reactivity of nitrogen towards the electrophilic species larger than protons. So, the presence of sterically hindered pyridines, they results in complete inhibition of polymerization in some system, but only lowered the rates of rates in other systems, you can say. Now let us briefly discuss about the activity of initiator co-initiator complexes, because once we form this the initiator co-initiator as we discussed in the previous slide, then we must assess about the efficacy of those activities of those complexes. So, the activity of initiator co-initiator complex is usually dependent on its ability to donate a proton or carbocation to the monomer, which in turns depends on the initiator, co-initiator, solvent, monomer. So, these four things play a very important role in the deciding the activity of this complex. So, the extent of formation of initiator co-initiator complex, that is sometimes you may refer the value of rate constant, that is K, and the rate of addition of monomer, that is the value of Ki in the various equations we have discussed. This generally increase with the increasing the acidity of Lewis acid co-initiator. So, Lewis acidity for various metals, this generally increases with increasing atomic number, so in each group. So, usually if you refer to the periodic table, it is represented as the vertical row of that periodic table. So, Ti is greater than Al is greater than boron, and Sn is greater than Si, etc. So, for any metal, Lewis acid acidity increases with increasing oxidation state. So, oxidation state is again a very important point of consideration while we discuss about the acidity concept of Lewis acid. So, it increases with the increasing oxidation. So, best example is that TiCl4 is greater than TiCl2. Sometimes ligands increase the Lewis acidity in the order of, say, fluorine is greater than chlorine is greater than bromine, then iodine, etc. The strongest Lewis acid is sometimes referred as SbF5. They are not always the most useful, since the result may be excessively fast and uncontrolled polymerization, or the reverse low rate due to the formation of excessively stable and inactive complexes between the Lewis acid and some other component of the reaction system. So, the activity of initiator co-initiator complex, this also increases with increasing acidity of initiator. Let us have an example like hydrogen chloride is greater than acetic acid, is greater than nitroethane, is greater than phenol, etc. in the polymerization of isobutyl with tin chloride. So, this is you can use or as a reference frame for polymerization of isobutylene. Now, a word of caution is always important in this particular cationic polymerization. This is regarding the generalization with respect to the order of activity, usually in a series of initiator or co-initiator. Sometimes it may differ depending on the identity of other component, monomer, solvent, or the presence of other competing reactions. So, sometimes the intermediates play a vital role, sometimes some byproduct may create. So, all these things need to be addressed during this particular process, and especially when you decide or when you discuss the activity of those initiator or co-initiator. Now, sometimes various industrial process being initiated with the help of halogen. Now, halogen, there are three basic halogens being used for the initiation step: chlorine, bromine, and iodine. So, they act as cations in the presence of the more active Lewis acid, such as trialkyl aluminum or dialkyl aluminum halide. Now, the initiating species is usually the halonium ion. Usually sometimes people may represent like X plus. This present in a low concentration via the equilibrium reaction between the Lewis acid and halogen. Now, iodine is usually unique among all the halogens available or all the halogens which we developed, that it initiate the polymerization of the more reactive monomers. One of the best example of these more reactive monomer is styrene. Apart from styrene, vinyl ether, vinyl carbazole, etc. These are maybe termed under this category of reactive monomers. Now, this can initiate the reaction even in the absence of Lewis acid. So, that is why it is termed as a unique, iodine is termed as a unique halogen. Now, it is not the actual initiator in the system. Iodine adds to the double bond to form a diiodide that eliminates the hydrogen iodide. So, the mechanism is quite simple, that it adds a double bond, then the diiodide form, and that eliminates the hydrogen iodide. Now, this hydrogen iodide, this generated by this process, act as the cationic gents, with the iodine acting as the Lewis acid to form the initiating system. Now, see, when we talk about this hydrogen iodide, this is not the efficient initiator, because iodide ion is too nucleophilic, and you see that we have discussed this particular thing in the previous slide. Now, the presence of iodine, this activates or sometimes dissociates the Ci bond sufficiently to allow the propagation to proceed. So, sometimes when you look into the after initiation, if you look into the propagation, then you need to look into this particular aspect. Now, this initiation route is more efficiently utilized by directly adding a mixture of hydrogen iodide and either iodine or metal halide, sometimes referred as ZnX2 or SnX2, to the reaction system. So, this is this you can say the add-ons to the reaction system. Now, sometimes the photoinitiation plays a very vital role in the cationic polymerization, and especially attributed to the carbon-carbon double bond. Now, the photoinitiation by onium salt and sometimes aryl diazonium or aryl diazonium, these are the non-nucleophilic or photostable anion. Sometimes they are referred as tetrafluoroborate or hexafluoro antimonate or SBF6, etc. Now, this hexafluorophosphate PF6, sometimes referred as PF6, they are effective photoinitiators of cationic polymerization. Now, photoionization is a very common technique in the cationic polymerization. So, sometimes the photonic energy being used to induce or initiate the cationic polymerization, but you require certain energy level, certain level of actuation to initiate that particular reaction. Now, aryl diazonium salts, they have a very limited practical utility because of their inherent thermal stability. Now, diarylonium or triaryl sulfonium, these salts are very stable, so stable that their mixture with highly reactive monomers, they do not undergo any kind of polymerization on long term storage. Some of these initiators, they have found commercial application in the photocross linking of epoxy resin through the cationic polymerization. Diarylonium or triaryl sulfonium salts, they act as a photoinitiator for various cationic polymerization processes. Now, this photolytic cleavage of ARI or ARS bond, they sometimes yield to the radical cation that reacts with HY to yield an initiator co-initiator complex that act as a proton donor to initiate the cationic polymerization. Again, we would like to reiterate the things that the basic concept of this particular photoionization or other protonic ionization, that you need to form an initiator co-initiator complex that further participate with the monomer to carry on these cationic polymerization. So, if you see this particular reaction here, these two, with the help of this photoelectric effect, they form the various complexes over here, and then they subsequently they may react with the monomer to initiate this cationic polymerization, or to be more precise, the with respect to the carbon-carbon double bond. Now, this HY, this may be a solvent or some other deliberately added substances, sometimes like alcohol, or sometimes this may have a water with a liable hydrogen. Overall the process is photolytically introduced the redox reaction between the carbon radical and HY. Now, interestingly, the same result has been achieved thermally without the photolysis by coupling the appropriate reducing agent, sometimes ascorbic acid or copper benzoate with dryryodium salt. So, this people have achieved this type of a thing with some alternate routes. The spectral response, usually referred as the absorption wavelength, absorption coefficient, quantum yield, photosensitivity, etc., and the thermal stability of this onium salt photoinitiator, this can be altered by modifying the structure of aromatic group in the cationic portion. Now, sometimes this particular approach is useful for doctored polymers. That means you can change the chain, you can change the various groups by either grafting or by some other means. So, the choice of the anion in the onium salt alter its behavior in polymerization by altering the identity of initiating species. So, cationic photoinitiators, they are used in coating, printing inks, adhesives, sealant, photoresist applications, where you can use sometimes these kind of photoinitiators are used to cross-link the thing, so that the mechanical strength among the polymeric chain or the surfaces can be improvised. So, they are having a very wide application in due course of time. Now, sometimes people may refer the other applications. These are involved the vinyl ether polymerizations, or sometimes the ring opening polymerization of epoxy monomers. So, as we were discussing that these may creature of the doctored polymers. Now, there are some differences between the radical and cationic photopolymerization. Now, the dependence on Rp on the light intensity is usually half order of radical polymerization, but first order for the cationic polymerization, the radical polymerization stops immediately on cessation of irradiation. So, this is the, you can say, the hairline difference between the radical and cationic photopolymerization. Now, most cationic photopolymerization, once initiated, they continue in the absence of light, because most of the reaction system chosen are living polymerization. If you recall that we discussed the living polymers and dormant polymers. So, usually when we talk about this cationic polymerization, then especially under the edges of photopolymerization, then we have to look into these living polymerization concept too. Now, let us have a look about the electro initiation process. Now, the electrolytic or sometimes electro-initiated polymerization, usually this involves the initiation by cations usually formed via electrolysis of some component of the reaction system, may be attributed to the monomer, solvent, electrolyte, or other deliberately added substances. So, the initiation in the presence of perchlorate ion Perchlorate ion is again very important for this cationic initiation. So, perchlorate ion usually proceeds by oxidation of perchlorate followed by the hydrogen abstraction. So, you see when we use this Hy as any kind of hydrogen donor, so we may represent this like this ClO4, and then we use any hydrogen donor, then it can give you this one. Now, this perchloric acid is usually termed as the actual initiating species in this category. Now, there are some electro-initiated polymerization processes under this edge. Some electro-initiated polymerization proceeds via monomer radical cation. Now, this monomer radical cations usually they are formed by electron transfer from monomer either to the anode or to a polynuclear aromatic compound. Now, usually when we talk about this electro-initiated, then propagation is usually proposed to proceed via dicarbocation formed by the dimerization of radical cation. Remember, this is slightly different what we discussed in the previous slides, previous concept, that is the radical, because electron transfer from monomer may be either to the anode or any kind of a polynuclear compound. So, let us take the example like CH2 double bond CH. Now, here this is the transfer of electron. Now, the radical cation being formed over here, and this is just subsequently converted into the dicarbocation, and by this way you can see the charge pattern. So, this particular aspect is again very important, and people are using this particular concept for carrying out various kind of cationic polymerization for the production of specific polymers. Now, let us have a look about another concept, that is ionizing radiation. Now, you see that in this particular chapter we are discussing all possible available tools for initiating, for propagation under the edges of cationic polymerization. So, ionizing radiation, this usually initiate the cationic polymerization. Now, the first event is the formation of a radical cation by the ejection of pi electron. Now, basic concept is that how we can generate this radical cation, maybe by photoelectric effect, maybe by some perchloric acids, maybe by any kind of radiating species. Now, here you may use some pi electrons. Now, the radical cation, this further can react to form other radical anion and cationic species. So, first thing is that you need to initiate this thing with the help of a pi electron, and then thus formed the radical cation, they can further react with the other radicals, sometimes other anionic species or a cationic species. So, whether one observes radical or cationic or anionic polymerization, it depends on the monomer and the reaction conditions. Now, reaction conditions sometimes may prevail about the intensity of those pi electrons, sometimes the radiation level of the media, and then the concentration and other things related to the reaction media. Now, one of the best example which we would like to discuss is that styrene. Now, this styrene can undergo polymerization by all three mechanisms which we discussed. For super dry reaction system, sometimes carried out at 25 degrees Celsius, the overwhelming mechanism of polymerization is cationic with about 2.5% anionic, and sometimes the negligible radical reaction. So, the radical polymerization becomes the dominant process with increasing the reaction temperature. Sometimes the presence of water, or you may say the other protogens, they decrease the extent of ionic polymerization relatively to radical polymerization. One of the best example of such category is isobutylene. Now, it shows the negligible tendency to undergo any polymerization except cationic, and that occurs only at you can say the lower temperature. Usually you need to carry out such type of thing below 0 degree Celsius. So, considerably below 0 degree Celsius is important in this particular polymerization process. Now, if you see the higher temperature, now see people have attempted to carry out this ionizing aspect at a higher temperature, but at higher temperature no polymerization occurs since the cationic reaction is usually not favored under these higher temperature. And sometimes people may ask that what is the higher temperature. So, always above 0 degree Celsius is referred as the higher temperature. So, the actual species, those who are responsible for the cationic polymerization, they initiated by ionizing radiation is usually not established as on date. The most frequently described mechanism, it postulates the reaction between the radical cation and monomer to form the separate cationic and radical species. Subsequently, the cationic species propagates rapidly, while the radical species propagate very slowly. So, this is the difference between the cationic species and the radical species. The former propagates very rapidly or fastly. The radical species or later one propagates small, is very slow, or you can say infinitely small aspect. Now, the proposed mechanism for isobutylene, because once we established the polymerization process or development of this cationic polymerization. Now, as far as the examples are in question, the best example as we discussed, that is the isobutylene. So, isobutylene, the proposed mechanism of isobutylene involves the transfer of a hydrogen radical from monomer to the radical cation to form the tertiary butyl carbocation and unreactive allyl type of radicals. So, you can see over here that this is with the help of a radiation, and you see that these are the polymeric reaction product which we are discussing, that this particular allyl type of things are practically inactive. So, at last when we discuss about the mechanism of this isobutylene, the evidence for this mechanism is based on mass spectroscopy of gas phase radiolysis of isobutylene, which may not be applicable to the typical liquid phase polymerization system. Now, initiation in sometimes we may refer to have a condensed system. So, initiation in condensed system may follow or sometimes follow the same course as electroinitiation, coupling of radical cations to form the dicarbocations. Now, cationic polymerization, when we say that it is initiated by ionizing radiation, usually markedly different from other cationic polymerization, in that the propagating species is a free ion remote from a counter ion. So, this is the difference with the or comparative note between the ionizing radiation induced cationic polymerization with other cationic polymerization. So, this is the basic difference between these two protocols. Sometimes overall electrical neutrality is maintained by electron trapped by the monomer. So, at last in this particular chapter or in this particular lecture, we discussed the cationic polymerization of carbon-carbon double bond with the help of several examples. Specifically, we discussed the common example. And since this cationic polymerization is extremely important in the development of a various industrial oriented polymers, so that's why, and we discussed all kind of initiation tools available as on date, maybe by the radiation initiator, maybe by the photoelectric radiations, maybe with the help of Lewis acids, etc. So, in case if you wish to have further study, we have listed one example, one reference for your further reading. By this way, we are summing up this particular lecture. Thank you very much.